Hello everyone, I'm recording this part later because we covered this in lesson 6 and unfortunately the recording didn't work, so some of you who were not in the class might have missed this. So this week we are going to work with raster. I don't think that storage will be an issue for anyone, but in case you run out of storage, if you're storing large files there, you may want to get rid of some of your old files. For example, if you have started the course from GeoPython first period, you might have some old files that you want to delete. Or at the end of this course, you probably want to keep your materials on your computer for future reference, because you know this NOP space will be available to you for another month or so, and then your files will be deleted. So if you want to keep a record of your files, this is how you do it. I already wrote about this on Discord, but here I will show you how to do it. So in the shared folder, I have added a text file, quick notes, and from quick notes you can copy this last line. So the idea is that we want to download files. You can easily download single files like this, but here you're working with directories, so it's not practical to download the files one by one, and you cannot download a directory as such. So if you want to download a certain directory, go to the right path, so where you can see the directory. So in this case, I want to export my AutoGIS folder. So here I have all my lessons and exercises, for example, or you can do this separately for exercises. Yeah, so I'm in the right directory. Then up here from launch, I open a terminal. So if you are already in the right folder here, then it's all good. But if you're not, then if you're familiar with Linux, you can just go to the right directory. But it's easiest if you're not familiar with Linux. It's just easier to just go to the right directory and be where you can actually see the folder that you want to export, and then start doing this. So I will just paste that one line of code. So it just converts or compresses your folder to a zip file. Well, it's actually a .tar, but it's a compressed file format that you can just download and unzip or uncompress on your own computer. So this is the name of the file that you want to create. So I will just call it AutoGIS 2025. You can name it however you want. And yeah, so what is the folder that you want to zip? So it's from here. So do you want to export this one or which of this folder? So I want to export the AutoGIS folder, so I will just update it here, AutoGIS, and that's it. You just run this. It takes a few seconds depending on how large, how much data, how many files you have in that folder. Then you will end up with a tar file, as you can see here. So I can already see the file. It's taking a bit longer for the raster files that we are working with in this week. They're a bit larger, but yeah, the process is done. You have your tar file here, and you can just download this to your computer and then just extract it, and you will have your lessons for your own record. So now let's continue with the actual contents of this week's lesson. Yeah, so welcome to the last week of the course. We made it. It's end of December, and this is our 7th week of automating GIS processes. Yeah, so I start by talking about the final assignment a bit. The information was already published last week, so I believe some of you have already looked at the materials, but I go through the main idea very briefly now. Then we continue with the topic for today. So yeah, so the goal of the final assignment is to practice and demonstrate the skills you have learned in the second part of the course. But of course, for many of us, many of us started with the first part course. So there's a time you are now more experienced with Python programming and doing data analysis in Python. So it's a good time to show off your skills. And the objectives are to show that you are confident in data acquisition, so you know where to get your data from, and of course data analysis. And we have talked quite a bit about data visualization
So it's also a good chance to practice how we can produce good maps in Python. Sorry for my voice. Like I might lose my voice at some point. I had a flu last week. But yeah, so similar to last period, it's okay to use AI and large language models, but with consideration. And consideration is that acknowledge it if you use it and go through the code, because like I was grading the GeoPython assignments, and most people had used them. But in some cases, I could see that the person has just copied and pasted the code without looking at it because it was just wrong. So make sure that you understand what is happening if you use it. And I recommend you to use it as little as possible so you learn actually what you're doing. Another important thing that many miss is documentation. It's a very boring thing to do. I'm personally not a fan of writing documentation, which is a bad thing. But please spend some time writing proper documentation. That can be in form of inline comments in your code or cells. Not only it's part of the grading criteria, but also it helps me to understand your code better, because there are 40-something students in the class, and I have to like go through each of the assignments. And if I read the documentation, I understand. So if you have used some smart solution, I may not understand it immediately. But if you look at your comments, I can understand it better and do the grading more properly. How do we do it? Similar as last period and every week, the same way as we have done the exercises. So it's on GitHub. There is a assignment that you can accept, but there is no template. It's just an empty GitHub repository. You just accept it, then you have a space to work in. One thing is that if your GitHub has this limitation of maximum 100 megabytes file size, so if you're working with a large data for your work, well, I try to use external sources. So if it's some vector data that you can get from WFS, to just use WFS. But if you really need to download the data, then don't put it on GitHub, because GitHub doesn't allow you to upload it. So you can use it in Notepad, but when you're uploading, you have a limitation with that. So do your best to avoid big data downloads. And if you open the repository for this, you will see at the beginning of the markdown file, there are two options, like submitted or I'm still working on it. So when you're done with your submission, just remember to check the submitted option. So I know you're done with it, then we can start grading. And the deadline is 6th of January. So we'll start grading after the holidays. Hopefully this will not ruin your holidays, so you can do it. Hopefully you will do it early enough. But the grading will start in January. I've already talked about this, but there are some exchange students or some who are graduating end of this year. So if you need the grade urgently, then just submit in time before the holidays and drop me an email, because I don't get notified when you submit. So if you're in a hurry, just drop me an email. Otherwise, we will get back to grading next year. So the ideas, we have given you a few ideas about the final project. You do not have to necessarily use any of these. So if you have your own data or some other idea how to do something, something else you want to study, feel free to use that topic. But if you have no idea what to do, there are a few suggestions here. One of them is called Access Squeeze, and the objective is to create a Python tool which can be in form of a Python script or a notebook for managing, analyzing, and visualizing the travel time matrix. Remember that in this course, in a number of weeks, we worked with that travel time matrix. And if you search the word, there are links on the website, but also if you just search, you can find the latest version of travel time matrix. So the idea is to create a toolbox that allows exploring the travel time matrix in different ways. And remember to use functions and different things that we learned during these two courses. Yeah, so these are the minimum requirements or some suggestions, things you should do. A file finder, a table joiner, a visualizer, and comparison tool. And there are other optional things you can include. Another idea is spatial anonymization. This is more on like geometry, shapely level of doing things. So creating an algorithm that would basically just displace points. So the idea is that you have a participatory data, so you have people's home locations, and you want to publish the data. Of course, it's private information. If you want to publish, you have to anonymize. And how do we anonymize points? Usually by displacing the point randomly to some direction. So using Shapely, you do that. So you create a random set of data, again with Shapely, and then you apply some displacement. And this is based on some article, and I've provided the links for you. So that's also one thing. And of course, you can work on your own topic, as long as you have the same components, kind of. You get your data from somewhere, you do some data analysis, and you have some proper visualization, maps and graphs if needed. Yeah, so be creative and work on whatever topic that you find exciting. Yeah, if you're in doubt, you can talk to me or drop me an email or write us on Discord if you're in doubt if the topic is good or not. But usually you find the right topic, so it's not needed necessarily. So some tips and tricks, best practices in programming. We have talked about those in the first part course, and there's a link here. But remember that we want to write codes that are for people, not computers. So if your code is just working, it's not usually enough. You should write a code that is readable. It's a generally good practice, but also in this case, we are going to read your code. So make sure your code is readable and understandable. Let the computer do the work. So the main motivation for many of us was to automate the processes. So try to do that as much as possible. Reduce the amount of work for yourself. Just try to automate the work. And we have learned different tricks how to do that using functions, using loops, and many other things. Do not repeat yourself. Yeah, so don't repeat code if not needed. For example, functions can help you avoid that. Yeah, and try to optimize, because now we are a bit more advanced with our Python skills, so try to write a better code. Handle the bugs in your code more properly and try to optimize it so the code runs more smoothly. Yeah. Yeah, so here's a checklist. I don't go through it, through this. Many of these things I mentioned already, but make sure that whatever topic you choose, you check the boxes for each of the items on the checklist. Yeah, so there are more details on the course's website. And of course, the feedback will be open, I guess, very soon. So please provide us with feedback for the course. That will help us a lot in improving the course in coming years. Yeah, so do you have any questions about the final project, or is it all clear?
So if we do our own cost-trigged efficient part, we already know it, or if we still decide like that, is it okay to inform the topic?
You don't need to inform the topic, yeah. Only if you're in doubt if it's good enough. But if you already know what you want to do, you don't need to inform. Yeah.
Is there a minimum amount of lessons that we need to use, or analysis examples from the exercises that we have to pull from?
No. Just show a general understanding of what you're doing. Yeah. And you can do this in pairs or alone. So if you're doing in pairs, there are instructions on the course's website. Please check them. But if you're doing it in pairs, it's enough if one person submits the code, but the other person still needs to accept the assignment and write a very short report, like half a page, saying that, okay, how did you work together and what was your contribution? But otherwise, it's enough if just one person submits the code. So, but it's optional. You can do it individually as well. Yeah, and we will be still available on Discord if you're before holidays if you have questions or if there's something to discuss. Yeah, so here on the course's web pages, there are very detailed information about the grading and some hints and everything you may need for your work. Yeah, so about the lesson today. So today's lesson is a bit different because we are not using GeoPandas anymore, maybe a bit here and there, but we are doing raster analysis. As I mentioned at some point, I guess the first lecture, this is a new addition to the course. So the course, we started covering this part since last year. So this is the second time. So it used to end at lesson 6. So we didn't have any raster material, but we added it because I believe that if you want to say I know how to do GIS in Python, you cannot say that without having some understanding of how to work with raster data as well. Depending on what you do, I personally mostly work with vector data because of my field of research. But for example, for some of you who might be working more with remote sensing, you might come across raster data quite often. So that's why we added this. And we have an exercise this week, so don't get confused with the numbering because we didn't have an exercise last week. So this week we have exercise 6. So we will be working with raster data, and I know that there is a lot of information here because we're working with new libraries. But hopefully you will learn something from this, and whenever you need to work with raster in future, this will be a good starting point. So I'm sure you will come back to this lesson later on if you need to work with raster. So even if not everything is everything is hopefully clear, but even if it's too much information, we can revisit this later on. Yeah, so there is it's a whole different ecosystem like raster data analysis, the libraries that we have. So that's why we could easily make a whole course working with this topic like raster. But now we have only one lecture on this. So that's why it might feel like there's so much information. But yeah, let's get started and see where we go. So we are going to work with 3 libraries today. Rio X-Array is the main one. Rasterio is a bit like, the main library in Python for working with rasters is Rasterio. So Rio X-Array is just a modern version building on top of Rasterio. So even if we will be only using this one, it is borrowing functionalities from this. So we will see this as well. And then this is actually built on top of this and this. X-Array is another library that works with matrix data analysis, like with arrays. So it's a mathematical thing. It's not necessarily about raster data. So it uses these 2 libraries. But we will talk about them more soon. The things we want to learn today, of course, we'll start by covering the basics, like how do you import raster data in Python, how do you read the values, and then we will see how we can do raster mosaic, so how can we merge raster tiles into a new bigger raster layer, and we will see how to clip raster layers, another thing that we often need to do when working with raster data. We will see how we can do reclassification with raster data, and then we will use our learning to conduct a terrain analysis. We will calculate the slope and work with elevation models and do some raster calculations. So that's the agenda for today. Let's go to Noppe. So the data is like, we are working with raster, so the files are a bit larger than before. So hopefully you don't run out of space. In case you do, remember that last week I showed you how you can download some of your data and free up some space, because the limit on Noppe is 1 GB per user. But at least I didn't run out of space, so hopefully it will be okay for everyone. So let's start with the notebook called named Raster Explore. So we start by exploring the world of raster in Python. So we all know what is raster, so I will skip that part unless something is unclear. Yeah, so most people recognize raster as an image, even if it doesn't always come as an image. It can be in different formats, but you can think of it as it's geospatial data that comes in this grid format. So you have cells that can be thought of as the pixels in an image, but also you might get your raster data as an ASCII text file as well. So it's not always a pixel, but that's the general idea. Yeah, so raster data represents the world as grid of equally sized cells or pixels, where each cell has a value representing information, and that information can be temperature, it can be the altitude at the place, and land cover, different things. So there are 2 well, it depends on how you classify raster data, but sometimes you come across single band raster data, so you have just one set of values for each pixel. So for example, elevation models are usually single band, so you have the altitude in each pixel. But sometimes they're multi-band, so for each pixel you have multiple values. And that's very common if you're working with satellite data, because they capture the raster or the image in different frequencies. So you will have a band for red, infrared, blue, and so on. So multi-band raster. So we will start working with the single band raster, and then we will see an example of multi-band raster and how to work with that. A key characteristic of raster data is a resolution, and it refers to the ground distance that each cell represents. And we are going to talk about resolution and use it a bit later on. You may get your raster data in different formats. Very often you get it as a TIFF file, which is an image file. It's a tagged image file format. That's what it's short for. But also, it's less common, but you may also find raster data coming in other formats, such as PNG or JPEG. And as I say, it can also be a text file in form of ASCII grid. But today we are going to work with TIFF format, and the idea is the same, so it doesn't make so much difference. The data that we will be, the libraries that I briefly mentioned already. So Xarray is a library, a powerful library for working with labeled, multifunctional, multidimensional arrays in Python. So it's about arrays. So if you're working with matrix, for example, this is a library that you will probably end up using. It's very powerful, but not necessarily for raster data. Then the world of raster was ruled by, in Python, was ruled by this rasterio library, which allows you to import data and do different kinds of operations, until this newer library appeared, and many people now favor this one. It's a bit more powerful, so it gets the functionalities of rasterio. So you can think of it as the GeoPandas of raster world, kind of. And so you import the data, write files, and so on from rasterio, but also you can do a lot of calculations using the this Xarray. So both of these are there. So one thing that makes working with raster data a bit tricky with Python is that, well, it used to be the same in vector world, but then came the GeoPandas. So as we talked about a lot, GeoPandas has a lot of things under the hood. So when you're working with GeoPandas, you are using Fiona for reading the files or writing the files. You're using Matplotlib for visualization. So GeoPandas came and put everything in one package. So it became a lot easier. With raster, we are still kind of missing that. So you load the raster using rasterio, but then you end up with this matrix that is a mathematical thing. Then you use this Xarray and other libraries to analyze. So it's a bit like you jump between libraries. Yeah, part of the reason why we have this gap in the libraries is that raster files can be quite versatile. Like compared to vector data, which is like predictable, raster can be a bit versatile. So yeah, so that's the reason we will jump between libraries during today's lesson. Okay, so enough of talking. Let's start coding now. So loading a single band raster data. So we will use Rio Xarray, and under the hood is using rasterio for reading the data. When you read the data, it loads the file into a data array format. So it's an Xarray data format. But yeah, let's just start and see how it works in practice. So we start by defining the path as usual. The next thing we are going to do is to import the library that we need. So we are going to use the Rio X array. Very often it's called RxAll, R, so giving it a shorter name for importing. The next thing I'm going to do is to define the path to my raster file. So everything is already saved in the data folder. So the raster file that we are going to work with is under data directory. And the file is called L41 33A, and the extension is TIFF. It's a TIFF file we are working. So the data that we are working with is an elevation model that we have downloaded from National Land Survey of Finland. So you know this data comes in tiles. So this is just one tile. I think from Nuuksio area. Yeah, so we are just importing one tile. So this is the path. So now we go ahead and import the data. So this is how you import a raster. So I will name it elevation raster. And the RioX array has a function called open rasterio. So even with the name, you see I haven't been very creative. So it's clearly telling you that the function is coming from rasterio. And the only thing you need to provide is the path to your file, which we have already stored under raster file. Yeah, so I have named this raster file. Oh, okay, yeah. Good that you noticed. Elevation raster, yeah. Let's just run this. Yeah, so the file is loaded, the raster is loaded. Now let's explore our raster file a bit more. So one of the things you can do is just to print the raster. So when you print the raster, it gives you some metadata, so some useful information about the raster that you're working with. So it gives you some information like how many pixels you have. So it's 3000 times 3000, like X and Y. You see the size of the file, like what are the values. You have float values and like for different, so different information about different bands. Like in this case, you have only one band, so you can see it's a one band raster data. Yeah, so a bunch of information. How many pixels you have is 3000 times 3000, so it's like 9 million of values there. Yeah, and you have a floating value, so it's the altitude which are stored as float in the data. So one important information here is the missing value. So all of you have experience with GIS, you know it's common with GIS data to use -9999 as the null value. So this metadata tells you that, okay, the missing value is marked as -9999. So we are going to work with the missing values later on in the second part. So yeah, so this is how you get some metadata from your raster. Another important thing that you may want to check is the coordinate system. So with the metadata, you don't get the coordinate system directly, but you can easily get it from Rio, again, coming from rasterio.crs. So this gives you some information about the coordinate system you have. So yeah, there's a lot of details, but probably what you need to know is either the name, which is at the very beginning, or the EPSG code that you can see at the end. Yeah, but it has all kinds of details. Yeah, so the data set that we are working with is already in 3067. But in case you needed to reproject it to another coordinate system, you could have just used this command. So you could have just saved it under a new raster, call it, use the function rio.reproject, and then you could have taken it to EPSG 3067. But in our case, we don't need to reproject. So let's just continue. So if you want to visualize your data, similar to what we have done with vector data, you can just use .plot, and it makes a plot of your raster. So everything in world of raster is a bit slower because the data is heavier. But you can see it's matplotlib again, then you use .plot, so you can change the visualization same way as we learned weeks ago. But yeah, using dot plot in most cases, you can create a quick visualization. And I will get back to why I say most cases. If you want to print some basic statistics from your raster, everything is typed in here, so you don't need to type. But you can just get some basic statistics of your raster. So you can get the minimum, maximum, average, median, standard deviation, and a few other things. So if you just run this, you will see the statistics. So this gives you an understanding of what kind of data you're dealing with. And you can already see that the missing value is minus 9,900, but it doesn't appear in your statistics because it already knows that those values are the null values. They're placeholders for null values. Okay, the next part is optional, but just quickly showing you that you can get raster layers or images from WMS. So we have worked with WFS before, World Feature Service. You know that there is also a web map service that delivers images to you. So this is an example of how you can get your raster layer or image from WMS. So there's a library that allows you to do that. So from oslip.wms, I've imported the web map service. So I just quickly go through this to give you an idea of what we have. Then you have a WMS URL, which you have gotten from the service provider's website. So that's the URL to Helsinki Map Services. And yeah, so with Web Map Service, you access the URL, and here's the version of the service they're using. Probably there's a newer one now. Yeah, so another thing that is useful is to list the number of the layers you have. Like with Vector, with WFS, for example, we could have looked at it in QGIS to see what kind of layers are provided. You could also check the service provider. But with WMS, you can just use these contents.items to get a list of the layers that are provided. So here I have written this extra part because in this service, there are a lot of layers. If I wanted to print everything, it would be a long list of prints. So I have just put this. So I'm just printing the first three when I run this. But there are many layers. So if you want to check what layers are available, you can use this. So I've just written a for loop going through all the contents.items. So contents.items gives you a list of layers. Yeah, but I put just 3 and then I'm breaking so we don't get the whole screen cluttered. So from this, I found a layer called this. So I'm going to use this for just an example. Then you can provide a bounding box. You can provide, so WMS can provide you the raster or the image in a number of coordinate systems. And this is how you can check the available coordinate systems. So I'm going to show you next. But I know that they can provide the data in 4326 if I want. The bounding box, the size of the image you want, the format, do you want some transparency, and then .read, and then with rasterio you just load it. Let's just run this. Remote disconnected. Yeah, so there's some connection issue with the service provider. Let's run it again. Did it work for anyone? Yeah, so I checked this already yesterday, it was working. Yeah, so they have some problem, but this should work. Let's try it again later. But if you want to, let's see if we can get this at least. Yeah. Yeah, okay, so this is not working, but it was working yesterday. We will test it again later at the end of the session if you remember. But this is how you can get your layer from WMS if it is provided through some service. And through this, you can see what are the coordinate systems that are available to you. So I will just show this from the courses website, see how this works. Yeah, so with WMS, this is the layer we were trying to get. And if you print the list of the coordinate systems supported, so these are the coordinate systems that you can get your data in. So you can use one of these. But yeah, that was an optional part, so it's not going to affect our work, luckily. Let's continue with loading a multi-band raster file. So with a multi-band raster file, you have different bands. So there are different, like it's essentially layers of images. It's more than one image. And that works a bit differently when you're loading it. So let's see how that works. So now we are working with another image. So it's a Sentinel-2 image from Nuxio. So it's a satellite image from Nuxio area. It's a larger tile to make it fit on Noppe. I've made it a bit smaller, so it's clipped. That's why it's called small. Originally, it was larger. So the file path is already defined here. So this is how I will load the data. So I will call it Nuxio Sentinel. So importing it is the same. So you use the same function, open rasterio, and you provide the path to your data, which we have stored here. So I will just copy the name. So Nuxio Sentinel, I'm using open rasterio to load it. So I loaded the data, but let's see what happens if I try to plot this. So let's just plot Nuxio Sentinel dot plot. So if you plot your multi-band raster, instead of an image, you will end up with this kind of histogram. So it gives you a histogram of the pixel values instead of the plot. So this gives you a clue that there are more than one band. And when you use that plot, it doesn't know which one to plot. So yeah, so we have a multi-band raster. To confirm this, I will print the metadata from my raster. So just using print. And yeah, this is a multi-band raster. So we have 12 bands in this raster file and a bunch of other information about the raster. Okay, so now we want to work with this a bit. So how do you know what is each band? Well, you get the information from the service provider. So here is the link to Sentinel-2 user guide. So there they tell you different things about the satellite images they provide. But also one useful information is what each band means. So I've gotten this earlier from Sentinel website. So I know that band 2 refers to blue. So it's the blue wavelength. So band 3 is green. And band 4 is red. And there are other layers. So depending on what satellite you're using, you have different kinds of bands. But what we are interested in is these 3 real colors, because we want to now create a RGB color, so we can visualize it as a rather normal looking image. So this is what we want to do. So we want to select just some of the bands and work with them. So let's see how we can use one single band. So I will call it, first I will start with red band. And from my Nuxio Sentinel raster, I will select a particular band. So from the metadata we have up here, I know that band 4 was red. So it's from the red wavelength. So I know it's from up here. So using .cell on a raster file that you have imported, you can select one particular raster band. So what you have now essentially is a raster that is single band. So now if you just try red band .plot, now it should work. So if you have multi-bands, then you can select them using .cell and providing the number of the band that you want to select. So let's try this for another band. So band 2 was blue. So I will try this for blue, but I will write the short a bit, code a bit shorter. So I will go with, again, I will select. This time I will select band number 2. And I will just plot it at the same time. So just in one line of code, I will select the band and plot it. So this is the same image, same raster, but in a different wavelength. So this is in blue. Okay, so next thing we want to do to exercise, as a little exercise how to work with different bands, is to create an RGB composite. So depending on what you want to do with the satellite image, you might be interested in different wavelengths. But now we want to just create a natural color image by combining the red, green, and blue bands. So creating RGB. So what we do, we just take the 3 bands and we stack them on top of each other. So we stack them together. So instead of having 3 separate bands, we will have a single band that has multiple dimensions. So to produce an RGB, I need red, green, and blue. So band 4, 3, and 2. So this is what we need. Okay, so for a stacking layers to create a composite, I will use a mathematical library that we have seen before, NumPy. So with raster data analysis, you end up using mathematical libraries quite a lot. So as I will import my NumPy as MP, which is very often used as a short name. So I will load each of my bands. So I will load my red band from this Nuxio Sentinel.cell, and the band number for red was 4. So I will just copy and paste this 2 times, just make some edits for each of the colors. The second one is the green band, and the band number for green was 3. And the last one was blue, and the band number for it is 2. So remember to also update the name of the variable. So now we are loading each band and storing it under a variable. Here I will have my composite image. So I will call it RGB image. From NumPy, which we just imported, there is a function called dstack. So it's just dimensional stack. So if you have different bands, you can bring it into one band, but make it multidimensional. So using the dstack function, I can create my composite now. So I will just put them values together. So red band has values, then green band dot values, and blue band dot values. So you can go ahead and visualize with this, but if you want to produce a rather realistic looking, it works better if you normalize your color values, because the color values that come from satellite directly, the range can be very wide. So to make the visualization look a little bit better, I will just normalize the values to 0 to 1. So I have a clear range, then the visualization looks better. So I will just normalize my values by just dividing what I have, RGB image, by the maximum value that I have. So I get the numpy max function and apply it on my RGB image. Yeah, so I'm dividing all the pixel values by the maximum. So I end up with a range between 0 and 1 that I can use, that makes my visualization look a bit better. But you could have tried it without as well. So let's just run this. Yeah. So for some reason, this works with double parentheses. I have to check one. Yeah, but now our composite is created. So what we want to do next is to plot our image. So I will import matplotlib. .pyplot, which we have worked with a lot, and I will give it a short name, just plt. And if you want to add a title, you can just add plt.title, give it something, RGB image. plt.access. I will set it to off. Many typos for one cell. But yeah, so this is a composite image. So we put the RGB together, it became a natural color image. It would have looked worse if you had just used it without normalizing. It looks better, but if you are curious, you can still make it even look better to make the RGB scales a bit more realistic. Okay, so this was briefly about the multiband raster files and how you can load them, and if needed, stack them up to create a multidimensional raster, for example, to produce an image, a real called RGB image of your satellite imagery. So now we want to get a bit more advanced and process the raster files a bit further and do some more advanced analysis. So we'll start by creating a mosaic. So as you know, raster files are big, but they're large files. So very often when you get your raster file from somewhere, for example, the elevation model from National Land Survey of Finland, there is not one image covering the whole country. It usually comes in tiles, because each of the tiles can be already, I don't know, hundreds of megabytes. So they're usually provided in these tiles. So what happens usually very often is that depending on where your study is, the study area might be split between tiles. So now we are going to work with the city center of Helsinki. And as it happens, the city center of Helsinki is divided in 4 tiles in the tiling system that National Land Survey of Finland uses. So these are the tiles. So I've downloaded the data from PyTulip. They're already there. So the tiles are coded. So these are the 4 tiles. And now in the first step, we want to put them together and create one mosaic, so one single raster. That might, depending on what you want to do with them, it makes things easier. So first I define the path as usual. Next thing I'm going to do is to import the library, RxArray, Rio X-array, and loading each of the data files, exactly what we did before. So nothing new here. Next thing I'm going to do is to check that all these tiles are in the same coordinate system. Of course, here I'm just getting the data from the same provider, so I'm sure they're in the same system, but just to be sure. Yeah, so everything is coming in 3067, and the assertion didn't produce any error, meaning that they're all in the same CRS. So next, let's just, everything is typed in. Let's just run this cell. It just visualizes the 4 tiles next to each other. So let's run this and see what we have. So we are just using matplotlib and using a subplot, something we learned in the first period, to just make the 4 tiles next to each other. Yeah, so this is the data that we just loaded. So we have each of these raster files. So there are 4 tiles from Helsinki Center. If you're familiar with the area, you may recognize how they fit next to each other. Yeah, so again, this is matplotlib. So for example, the subplot that we learned in the last period can work here as well. So you can improve the visualization however you want. So now let's get to the fun part of creating the raster mosaic now that we have imported our data. So from Rio X-array, I'm importing a submodule called merge. From there, I'm importing merge arrays, a particular function. So importing the whole thing, I'm just importing the one function that I need. So I will create my mosaic and store it under a variable called mosaic merged. And for doing that, you just use the function that you imported. So it's merge arrays. It's the name of the function. So as the input, you provide a list of the tiles that you want to merge. So we had raster 1, we had raster 2, raster 3, and raster 4. Here I've commented this out, but if you want to save it, this is how you can save a raster. So you can just use rio.toRaster and provide the path and save your raster. But I don't want to save it now because it takes a space. So I've just commented it out. But instead, I will just visualize our mosaic. Yeah. Raster. So remember to save your file every now and then, because it can also happen that it runs out of memory and crashes or something. Yeah, so this is our merge raster. So we put the 4 tiles together. Now we have a single raster file to work with. So there's a mosaic of those 4 tiles. So this is something that is very often useful, depending on what kind of analysis you want to do on your raster data. Another thing that we often end up doing when working with raster data is clipping. So you have a polygon. For example, in this case, we imported data from Compi. We have imported data from Helsinki Center. And now next we want to clip it to just include Compi area. So let's clip our raster with a polygon. So what I'm going to do next is to just get the boundary of Helsinki from WFS. So I'm just using the Helsinki City service, and hopefully this works. It worked. Yeah, so this is just WFS. I'm getting the border. If you had it offline, of course, you could have just loaded the data. So this has the official boundaries in Helsinki. So I want to just get the COMPI area and just use that single polygon to clip my data. So there are a number of ways how we can choose it. You can go by name, but the name is a bit like specific. So the easiest way is to just go with the postal area. So we know that the postal area of the COMPI is 00100. So from this data that I just loaded from, downloaded from WFS, I will select the polygon for which the postal area is 00100. So there's nothing new here. It's a good old GeoPandas. So it's COMPI. I will then take my coordinate, take it to the same coordinate system as my raster files because I want to do a clipping, so they should be in the same coordinate system. So this is coming in 3879, but I know that my raster is in 3067, so they're not matching. That's why I'm doing this transformation. So I take my COMPI polygon to the same coordinate system as my raster, and then I plot it. Let's just plot and see what we have. So this is the boundary of COMPI neighborhood. We have seen this before in one of the lessons. Was it last week? So now I'm going to use this polygon to clip my raster. And this is how you do the clipping. So first we have an assertion that is a bit redundant because we already transformed it to the right coordinate system. But as a good habit, we are just making sure that it's in the right, they are in a compatible coordinate system, in the same coordinate system. This is where we do the clipping. So I will save the output as clipped mosaic. So the raster that I want to clip is the mosaic I just created. So it was called mosaic_merged. And for clipping, there is a function called rio.clip. So what it needs as the input is the geometry of that polygon. So from my COMPI layer, I specifically point to the geometry. It also wants you to provide the CRS that you're working with. So again, that is easy. From COMPI, I just use the CRS. Again, if you want to save the output, you can save it using rio.toRaster, but I will skip it to save space. Yes, thank you. So, geometry. Yeah, so now we clipped our data. You can see that the shape of COMPI appeared there. But there's something wrong. Can you guess what is wrong? Because we are working now with, this is elevation model of Helsinki, like Finland, so from COMPI. So you have values here, but you don't really see them. And then instead you have this dark blue area outside. Probably have encountered something like this in QGIS or ArcGIS as well. So what you are having here is that, okay, now you have clipped, so this has become essentially null value. But the Python, the library, doesn't recognize it. So it's just applying, this is, for example, -9999. So it's visualizing that as a color. And then you have these tiny differences here. Like Helsinki center is not, the altitude doesn't change so much. So compared to this, you're losing that altitude differences here. So anyway, the problem here is that we don't have, the missing values are not masked out. So we want to mask them out. So that's the next thing we want to do. Okay. You remember that when we were printing the metadata, we could see the no data value. So what value is recognized as no data? Is it -999 or something else? So what is the no data value? I can get it straightly from my raster data. So from my clipped mosaic, I can get from Rio the no data value. So these are no data values. Are they null? Are they minus something? It's some arbitrary value. They usually get from metadata, but you can also read it from the raster if it is defined properly. The next thing I'm going to do, I'm going to mask those null values. So I don't want to visualize them, so it doesn't mess with my visualization. So this is how you mask. So clipped raster is what we want to work with, our layer. So let's write this, then I will come back and explain. So clipped underline mosaic. Okay, so now the visualization looks better. So what did we do here? We identified what is the missing value, and then we used a function, a var function that is coming from NumPy, a mathematical function that we have seen before, to mask out the value. So how does the var function work? So it's numpy.var. So you have a condition here. So you can set a condition. If the condition is met, if it is true, this will be the value. So you put a condition. If the value is null, replace it with this. If it is not null, then this will happen. So this is how the var function works. So here is a simple example of it. So with NumPy, you have an imaginary array. So you have values 1, -2, 3, -4, -5. Then you apply var. And your condition is that if the value is greater than 0, just keep it as it is, the original value. If it is minus, then it will be replaced with 0. So what you get as the output is that all the minus values are replaced with 0. Does this make sense? Do you see how this works? Yeah. So a form of this is to use this implicit masking. So this is what we used. So if you do not, you can just write the full thing, or you can go with the short version. So if you go with the short version, this implicit masking with xarray, what happens? This is what we do, what we did. Elements satisfying the condition keep their original value, and elements that fail will get the null value. So what we are doing, we are replacing the missing value, whatever it was -9,999. We are replacing it with a NumPy null value, so NaN. Do you remember, like in the last period, when we were going through the pandas, we were replacing the arbitrary like -1 with like null values. So Python knows that this is a null value. So this is what we are doing in this part. And when you play with it a bit, you will work with this in your exercise. It will start to make more sense. Yeah, but working with raster data, missing values are a big issue, so we have to handle them properly. Now we move on to the next thing, which is raster classification, reclassification. So very often you get your raster with certain values, but you want to reclassify it to something else. So the first thing I'm going to do is that, okay, I want to print the range of my data. So in order to reclassify, I want to have an understanding of what is the range of values that I have. So this is still the elevation model that I'm working with, the same clipped raster. So from my clipped raster, I want to see the minimum values and also the maximum value. So I want to get the range. So clipped raster dot max dot values. So now I know that my elevation in COMPI area is ranging from almost -2 meters all the way to 32 meters, roughly. So this is the range, and this can give you an idea how you want to So we have two ways of, as we have seen before, we have seen classification before, and you know that you can do the classification manually or use some of the built-in classification methods, so using map classify library. So we can do the same thing with raster. So in the first example, and everything is typed in, so I will just briefly go through the code and say what is happening. Okay, so in the first, well, I'm importing the NumPy. I'm importing the X-array. So here I'm working with the X-array, so the library that is meant for managing arrays. So I'm defining my bins. So how do you want to do classification? So I want to put everything from -10 to 10, and then to 20, and then infinite, like anything bigger. So I could have put just some large number, but you can put NumPy infinite to just anything. And in this case, I know the maximum is 32, but anyway. Then some values that you want to assign, so you're reclassifying. So you classify them and you give them a title. So the first class will be called 1, second class is 2, third class is 3. So these are the new. Next thing I'm going to do is masking the null values again. So when you're classifying, you should be sure that they don't end up in your classification. So this is a bit redundant because we had done it before, but it's a good habit because you are doing the classification. Make sure you handle the missing values. So I'm replacing the missing values with a NumPy none, NumPy null. So next thing I'm going to do is to do the reclassification. So this is how you do the reclassification. Yeah, so this negates, it makes the logic opposite. Because this will return the value. So if it is null, it will be true. So you want it to work in cases where it's not null. So you're negating the thing. So with Python, this is negating the process.
It's not the information.
No, that's for like, it does the same thing, but it's for like Boolean values. You can turn true to false or false to true, but same idea. Yeah. So with Python, this can turn a true to false, a false to true. So with Boolean values, it negates it. Then with NumPy digitize, I'm using my masked raster. So we already got rid of the null values, or we didn't get rid of them, we just masked them. I'm providing the bins that I defined up here for classification. And you can set right to true. So what does it mean? It means that, well, you have this 10. So if a value is 10, is it in the right bin or the left bin? If you set the right, to true, it will fall into the right bin. So they overlap. So 10 is in the second class, 20 is in this class, so to the right one. So you can set it as true or false. If you set it to false, it will go to the left bin. So again, doing the same thing on my reclassified data. Again, in case there is some missing value, I want to make sure it doesn't appear in my visualization. The next thing I'm going to do is to convert it to a data array. So you have to reconstruct your raster again. So you remember that the raster is an array essentially in Python, and it's a multi-dimensional one because you have multi-dimensions in raster. So that when you are working with NumPy, you are kind of destroying that raster format. So I'm just reconstructing it. So I'm converting it to a data array again and using the structure, the dimensions, coordinates, and attributes of the original data. So let's just run this. So the reclassification is done. Let's just visualize this. This is just matplotlib and just some formatting details. So now you reclassified your values to 3 classes. So you have low elevation, medium elevation, and high elevation. So this was just manually. So you defined your bins manually like this as a list. What if you want to just apply like natural breaks or some previously defined classification? So for that, you can use the map classify library, but it's a bit less straightforward than when we used it on vector data with pandas. So what you have is that map classify, so your data is multidimensional. So you have a matrix. You don't have a list. It's like a matrix. It has X and Y. So map classify doesn't work with a matrix. It just works with a list of values, like we saw in pandas. In pandas, we were just working on one column. So what I'm doing here is that I'm flattening my matrix. So there's a function called flatten. So it just makes them one list. So you have a raster with pixels on each row. It just makes it one list. So it puts everything in one line. So this is what flattening does. So you flatten it, but you want to keep the shape. I want to reconstruct my raster. I don't want a single line. I don't want the list. So this is how you're going to store the shape. So from clipped raster, I'm storing the shape using dot shape in the original shape. So this stores the shape. It knows that, okay, there are like 100 pixels, then it goes to the second line, then it goes to the third line. So it maintains the shape. Then I'm masking the values, the null values. And here I'm applying the natural break. So this is map classify. We saw this already weeks ago. So I'm applying this to my flattened array, from which I've removed the null values already. And this is a natural break, so you have to provide the number of classes you want. So I'm going with 7. And then from here, remember, from map classify, you could access the bins. So again, we are doing the classification here using the same method. But if you want to apply natural breaks, you can produce these bins that we defined manually before. You can just create it with map classify. Then we end up with bins. So it's exactly the same as what we did up here. So we have the bins. The rest is just the same. So we go with np numpy digitize. We apply the classification. So one thing that has happened here is that, I know this is a lot of information, but once you go through it a few times, you will see what is happening. So you remove the null values. Then you do the classification. So what happened to those null values? Those were pixels. You cannot just get rid of them, because when you're reconstructing your image, you have some missing pixels. So that's why we are using a NumPy function called full-like to create a. So we had a raster with pixels like this. Then we did some reclassification. And in the process of reclassification, we removed the ones that had null values because they would have messed up with my classification. So now I did the reclassification. So I know this is category 1, this is 2, this is 2, this is 3. So we did our reclassification. Now I want to reconstruct my image, but I've removed these things. So I don't have it. So NumPy has a function that can recreate this structure with whatever value you want. So I'm going to recreate this with null values. So I will apply null values to all of them to get the pixel structure. Then for those that I have a value, like here I know it's 2. So I will replace it with 2. Here I don't have a value, so it remains null. Do you understand what we are trying to do now? We want to get the full picture back. So we create an empty picture with only null values. And then we check. Wherever we have real values, we replace it with real value. Otherwise, it remains null, which we can then visualize. So this is what we are doing here. So NumPy has a function, full-like. It creates you this. It creates you an empty, or not empty. It just creates you an arbitrary raster with whatever value you want. So this is the value I'm using. So I'm applying null value to all of these pixels. And wherever we don't have the null value, so wherever it's not none, so I have the negation here. Wherever it's not none, I will use the classified raster values. So wherever we don't have none, I'm reading those real values that I have. So I'm reconstructing that raster. And then I'm using the reshape. So with reshape, I'm bringing back the original shape of the raster to the dimensions. And the rest is just the same as before. Let's just run this. Yeah, so you reclassified your data using map classify. So there are a few steps to take, but if this is something you need to do often, then you have these pieces. You just know how to reproduce this later on. So with reclassification, as we saw already in week 4, if you have null values, it's problematic. That's why we have to take those steps, because they just end up in one of the classes, then things get ugly. Okay, so that was the less fun part, the reclassification. What is a bit more interesting is to do raster calculations. So those of you who remember older versions of ArcGIS, this was called like map algebra. I guess now they have renamed it to raster calculation. Yeah, but we want to see how we can do some raster calculation. The point here is not to learn how to calculate the slope, but we are just using the slope as an example of how to calculate things with rasters. So slope analysis is a key terrain analysis technique used in GIS and spatial analysis to measure the steepness or incline of the terrain at any given point. So we want to use our digital elevation model to calculate slope. So I'm sure you know what is a slope, and if you want to learn more, there are a lot of good materials out there. But what we essentially need is this. So this is the formula we are using for calculating the slope. So essentially just calculating how much you are losing or gaining altitude in a certain amount of distance. So you're calculating the steepness. So we want to calculate this just as an example how to do calculations on raster data. So the data is coming. Of course, we could have continued with the data from COMPI, but we don't have so much altitude, so it doesn't make sense to calculate the slope. So I got data from a hill in north of Finland, Ylläs. So the data is coming from there. And this is what we want to calculate. So let's load the new raster data. So it's another tile from the same source, National Land Survey of Finland. So let's just run this cell. So what we want to do is to calculate the slope. So how do I want to calculate the slope? So I have a raster data. And, well, I'm limited by the resolution I have. So I know the resolution of my raster. I guess it's like 2 meters. So I know it is 2 meters. So from the center of this pixel to the center of this pixel is essentially 2 meters. And for them, I have the altitude. So I know it's like 100 meters here. Here is 110 meters. So I can see that it loses or gains 10 meters in 2 meters. So that can allow me to calculate the steepness. So just simple mathematics. Do you know what we are doing? No. So I'm going to use the resolution of my pixel, calculate the altitude difference between the 2 pixels, and just calculate the slope. So let's do that. So I'm going to get the X resolution. So to calculate that 2 meter distance, I know it, but I want to get it from the data. So I will call it XRes. And it's coming, I will read it from my Ylläs data. So it was stored Ylläs._dem. And how can you get the resolution? From Rio, you get the resolution. So it returns to you a tuple. So the first value in the tuple is for X, so the resolution in X direction. So I do the same thing for the Y resolution. It's a grid of equal size, so it's the same, but just to be correct, I'm getting them separately. So doing the same thing from my DEM, I use Rio.resolution. But this time I read the second item that is returned to me, so index 1. Okay, so now I'm going to calculate this. So I'm going to use this formula and do that calculation. So I will do. So let's calculate the amount of altitude that is changing in X direction. And for calculating the difference between pixel values, there's a function. So our job is easy. So it's a function called differentiate. So I just use differentiate. So hopefully I don't have typo. And here I'm calculating the pixel value change in X direction. So for chord, I provide the value X. So it calculates it in X direction. And remember, we want to divide it between the to the distance between pixels. So it was called X resolution. So I'm dividing it by X resolution. So it's the gradient in X direction. So we can repeat the same thing for the Y direction. Just remember to rename the variable. And the chord here is Y. And here is Y-res. Okay, so we have calculated these two, this one and this one. Now we have to take it to the power of 2. So this was the formula. So for calculating the slope, from NumPy I used the SKURT. You could have used the math SKURT, doesn't matter. So this one to the power of 2 plus to the other gradient to the power of 2, dz dy to the power of 2. So now I calculated my slope. To make it make more sense, I want to have my slope in degrees. So again, this is just mathematics, not necessarily Python. So I'm just doing some math to convert my slope to degrees. So once we do the calculation, we should update the raster attributes. So slope. So now what we want to visualize is, well, the value we have, the attribute we have is a long name. So it's the information that is built into the raster. So the attribute is the slope, what we have. You should also provide the units that your data comes in, so it's degrees. Okay, so I'm sure I have some typo somewhere, but let's try. Yes. Yeah, thanks for noting that. Let's just hope that I don't have typo. Okay, I guess I didn't. So now let's visualize and see what we just measured. So this is a bit of mathematics. If depending on what background you're coming from, you may not be super comfortable, but the point here is to show you that you can do math on raster. So this was about the slope. In your exercise, you will be working with temperatures, so idea is the same. So this is the slope. So you're looking at that hill, and this is the slope. So it looks quite nice. So I want to just one last part. So we learned how to calculate something on the raster. So we had a raster, we just calculated something, some mathematical thing. So in your exercise, for example, you will convert, you have a raster of temperatures, you take it from Celsius to Fahrenheit. But what if you want to do calculations between rasters? You have two rasters, you want to multiply them. So you want to do map algebra, as Esri used to call it. So is there anyone here who has never done map algebra or raster calculations in QGIS or ArcGIS? Most of you have done it. So it's just you have two rasters, there are two matrices, you just multiply them, you can sum them up depending on what you're trying to calculate. So the example we are going to use is a measure called SSI. Yeah, so it's a slope stability index. Something I've never personally used, but SSI is calculated like this. So it's 1 divided by the slope multiplied by elevation. So this is just an example. So what we want to do is to multiply the two rasters we have. So we have the elevation model, we have the slope we calculated, we just multiply them and then 1 divided by what we calculate. So just as an example of how we can do this, Yeah, so this is how you do raster calculations in Python. So I will load the data sets that I have, the layers that we have. So they're already loaded, but just to have a complete cell. So slope, they're not multi-band, but just to be sure that I get the first band, it's a good habit to use the index. So I will just get the first band of my slope. Anyway, it has just one band. I will do the same thing. I will load my dem. You don't have to provide the band, but in case you're working with a multi-band, it's a good habit. So we are doing a division here. So the one thing you want to avoid is division by 0. And that can happen when you're doing division. So what I'm going to do is to leave out places where the elevation is 0, so I don't end up with infinity. So let's just filter our raster. So this is how you can filter values. So from the same dem, I use the var function that we saw before, keeping values that are greater than 0. So I'm essentially masking everything that is minus, in case there was a minus in the data. Probably not. So now I got rid of the 0 values. This is where I calculate my output raster. So we already looked at the formula. So it was 1 divided by the multiplied of the 2. So it was the slope times dem. So this is how you can do raster calculation. You can just multiply the slope times dem. As easy as that. Yeah.
What do you do with the dem? Because we less dem, then aren't we using the dem? Like we first name the dem to just press the first band, but then shouldn't we do the where also on the dem?
Yeah, we are replacing it. Yeah.
But then shouldn't it be the new one that we use the where on? So should it be just dem dot where? Or?
Well, this is the new one. We are replacing it here. So it's
You already assigned that
But
variable.
then the previous line is redundant, right? Because we are again using the old one. So that because we're doing plus dem dot where, which
Yeah.
means that we don't care anymore about the dem we created.
Yeah. Okay.
Or maybe it doesn't make a difference because it's
Let's see. Yeah. 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 Good point. Let's go with dem dot where. Yeah. Yeah. So I calculate the slope as SSI. Probably I'm not ending up with any infinity because we handled the zeros, but just in case there is a case like that, I will mask them. So from SSI, I use the same function where. And in case I've ended up with an infinite in one of the cells, so its numpy is infinite, so it's handy. So if I have a case where the value was 1 divided by 0, I will just replace them by non-values, because it doesn't mean anything in my case. Okay, so here we are calculating the SSI using the formula, and in case there was an infinity, in case 1 was divided by 0, we replace it with null value. And here it's an optional part in case you want to save it as a TIFF file. This is how you would do it. Just so when you want to save it as a TIFF file, this is the order of the data when you're working with X array. So it's band Y, X, the order of the information. When you want to save it as a file, like as a TIFF file, this is the format it expects. So band, so this is what is expected, but sometimes it can be the other way around. With X array, it's the other way around. That's why I'm checking here, and if needed, I'm transposing it to this. So in case you try to save it, you might get an error if you don't do this. So you transpose it to band YX. So this is the order of how the data is stored in the array. And then you can save it here. But I'm not going to save it. So I'll just comment that out. So let's just run this. It's finite. Finite. It's not infinite. Yeah, it's finite. Yeah, it's like this. It's finite. Yeah. Okay, so let's run this a few times. So what is happening sometimes with raster, depending on what library is being used, there's a thing called lazy loading. So the Python rushes to visualize something before it's fully calculated. So you end up with that wrong raster. So now I reran it, and the second time it looks correct. So that can happen sometimes with raster. So the calculation is happening, but Python rushes to visualizing it. So you end up with a corrupt raster. So this is what we ended up with. So you have the slope stability index calculated. Yeah. I know there was a lot of information, and many things might be confusing, but you get to practice them in your final exercise, and we will be there on the Discord in case there are some questions. We will help you out. And of course on Friday. So if there was something unclear, once you go through this, you will probably come up with more questions. So I recommend you to go to the help session on Friday. Yeah, and that was it. Thank you very much for this whole period, and see you hopefully in other courses.